Hello class. In this video, I want to just to give some tips about some couple of exercise that I noticed has been a little bit challenging in your homeworks, and I want to comment about that. Now, those exercises are related to module number 2, part 2, okay? Which is the continuation of derivative, basically sections 3.6 and 3.11. And basically the two exercises that I want to comment, that I want to make comments about, is one is from 3.9 and the other one is from 3.11. Just a reminder, okay, tomorrow, August 8th, which is Thursday, okay, is due all the homeworks for the second part of chapter 3. Okay, so that is due tomorrow. So that's why I want to comment that. And remember that over this weekend, between August 10 and 11, you will have in my lab map open the first sectional test, which is basically about these two. So I just want to comment about those exercises, okay? Because those exercises are very important. Okay, and also one of the exercise, and both of the exercise is in your lecture notes. Let me just open that. In this video, I'm going to comment just one because I don't want to make the video so long. And then I'm gonna make a second video that is gonna about the second one. Okay, so the title of the videos is gonna be Tips for Exercise on Sections 3.6 to 3.11, something like that. Okay, so let me open this one. The first one is this. Okay, so you have here a function that is one function raised to another one. Okay, so let me put it here. So you have here a function fx, which is one function, let's say g x raised to another function. I'm going to call the other function h. In this particular case, g is the sign of x and h is the natural log of 9x. When you have problems like this, in which you have a function raised to another one, and they ask you to compute the derivative of the function, okay, the derivative of the original function of this function, in this case f, the trick in here is to express the base as an exponential function. Okay, and let me just make some opening here. Okay, let me just make some space here. I'm so sorry. But the trick is to express this function, which is the base function, as an exponential one. And we're going to use the fact that the natural log is the inverse of the exponential function and vice versa. You know that already. So we can write down just that. We can write down gx in the following way. The exponential of the natural log of gx. Okay, so what we are doing here in this expression is evaluate the exponential in the natural log. Now, because the natural log is the inverse function of the exponential, that evaluation is going to be the argument. It's going to be the argument. So we can express GS in this way. And that's what I did here. So in this case, GS is the sign of S. So sign of S can be expressed as the exponential rise to the natural log of sine S. So this is exactly the same what I have over here. And that is, this relationship is valid for every function. Okay? Assuming that, of course, Gx is going to be evaluated in points that belongs to the domain of the natural log. Okay? Perfect. So if we have that, then the function f is going to be expressed as an exponential function. You see here, we have the exponential of the natural log sine S, everything rise to the natural log of 9x, okay? Because this is equal to this one. Now, the advantage of this is that now we express f as a power function, in which the base, instead of being a function, now is a number. And that's what we want to have. Okay? Now, we have here properties. We need to use here properties of the powers. Okay? We have a power, which is this one. This is a power because we have the exponential of something here. Okay? So we have power to a power. So we have one power rise to another power. So what is that? When we have power to a power, well, we keep the base, and we multiply the exponents. So now we have the natural log of 9x that multiply the natural log of sine x. So this is the first simplification, or a way to rewrite the original function, this original function here, this one. Okay, fx, which is fx. Now, well, we compute the derivative of this one, but the derivative of this one is very easy to compute, because the derivative of this one is the composition of functions, is the exponential functions composed with some function that in this case is a multiplication of two other. So if you apply the chain rule, this is the derivative of the exponential function evaluated in the inner function. That's what I have here, which is the exponential function itself, times the derivative respect to the variable of the inner or internal function, which is the derivative of this multiplication. Okay? But you know how to compute the derivative of that multiplication, right? So this is the derivative of the first one, which is this one here, times the second factor, and then the derivative of the second one, which is 1 over sine times the derivative of the sine, which is the cosine, times the second factor. So I apply to compute this derivative, I apply the chain rule again. And then what it follows is just a simplification. Okay, but the tricky part is to know that whenever you have expressions like this, you can express the base of the function as exponential function. in this way. So you use the fact that the natural log is the inverse of the exponential to express this guy in this way. Okay, that's the comment that I want to make. And well, you compute that derivative, and at the end, the expression that you're gonna get is this one that you see over here. So you need to make the simplification, but I'm not going to go through that because that part is very easy. Okay, and the second part is just to evaluate the derivative in s equal to pi over 2. And that's it. Perfect. Well, thank you.